Let's go ahead and excuse me, get started. We're going to work a series of problems all involving the iron carbide phase diagram. And we're going to work really with three different areas, three different tie lines. I'm going to get my pen going here. Sorry about that. All right. We're going to work below the eutectoid temperature, which is 727. And if we do that, we'll use this tie line, which has the value of 6.7, the weight fraction of cementite on one end, and 0.022, the weight fraction of carbon in ferrite over here on the left end. In some instances, we will also work with the tie line just above the eutectoid temperature. That involves austenite and pro-eutectoid cementite, the cementite that forms above that eutectoid temperature. Similarly, we might use the tie line in this region, which involves austenite and pro-eutectoid ferrite. So just depending on the system concentration of carbon, we'll be using one of those three tie lines to help us get the mass fraction of the phase that we're interested in. And we'll, if we come through the eutectoid temperature or the eutectoid composition, it will be a eutectoid steel. If we have carbon concentrations greater than the eutectoid, we'll refer to those as hyper-eutectoid steel, and less than that carbon concentration of the eutectoid, we'll refer to those as hypo-eutectoid steels. So let's go ahead and get started here with problem 9.57. We're asked to compute the mass fractions of ferrite and cementite in perlite. Let's look at the diagram here. This is the figure 9.26, showing the austenite decomposition from point A to point B, giving us 100% perlite in this case. And so we're going to work with this tie line here at just below the eutectoid temperature, extending across from point B. So back to the problem, we were asked to calculate the mass fractions of ferrite and cementite in perlite, and we can do that by recognizing that tie line I just mentioned. And since it's a eutectoid steel, we know the system carbon concentration is 0.76. We can calculate the mass fraction of ferrite then by defining these two lengths on either side of that eutectoid composition. And remember that when we use the lever law, we use the numerator is the length of the opposite side of interest. So we're interested in calculating the fraction of ferrite in perlite. So that will be L1 divided by the total tie line length, L1 plus L2. So we can plug in those values. And calculate that the mass fraction of ferrite in perlite is 0.89. We can write a similar expression for the fraction of cementite in perlite using L2 is in our numerator now instead of L1, same denominator, and calculate that the mass fraction of cementite in perlite is 0.11. Of course, if we did this calculation correctly for the mass fraction of ferrite, we could calculate the mass fraction of cementite straight away by just subtracting 1 minus that. But in this case, we've done both calculation and confirmed that indeed they're correct. So the mass fraction of ferrite is 0.89. The mass fraction of cementite in perlite is 0.11. In problem 9.59, we're asked what is the carbon concentration of an iron-carbon alloy, excuse me, for which the fraction of total cementite is 0.1. So let's take a look at this in terms of the phase diagram. Once again, we're going to use the entire iron carbide phase diagram to help us solve this, and we're given in this case the mass fraction of cementite is 0.1, and we'll have to calculate the system composition. And we'll see this nomenclature come up here several times. When we talk about total cementite or total ferrite, that means we're working below that eutectoid temperature. And with this tie line, bounded on the right by 6.7, representing the carbon concentration of cementite, bounded on the left by the carbon concentration of ferrite, which is 0.022. And in this case, we have an unknown system composition that we need to calculate. But we're given that the mass fraction of cementite is 0.1. I'm going to define my links on both sides of this unknown carbon concentration X as L1 over L2. And since I'm interested in the mass fraction of cementite, I want to use L2, that distance on the opposite side of the tie line, and then my total tie line length is L1 plus L2. So in terms of those lengths, then L2 is x minus 0.022. The total tie line length is 6.7 minus 0.022. And we can go ahead and solve for x then and get a value of 0.69% carbon. Which is a hypoeutectoid steel, meaning its carbon concentration is less than the eutectoid by just a little bit, of 0.69% carbon. In 3.9, in problem 9.61, we're given that we've got 3.9 kilograms of austenite and contains 0.95% carbon, and it's cooled to just below the eutectoid temperature of 727. A, we're asked what is the pro-eutectoid phase. B, how many kilograms each of total ferrite and cementite form. C, how many kilograms each of perlite and pro-eutectoid phase form. And D, schematically sketch and label the resulting microstructure. So let's take these first, or take these one by one, first starting with what is the pro-eutectoid phase. We're going to use figure 9.32 as our example here. We're at 0.95% carbon, slightly less than this particular figure, but because it is a hyper-eutectoid steel, all of the schematics are relevant. We're just slightly to the left of the example figure. So the pro-eutectoid phase that forms is cementite, and the schematics of this decomposition would be essentially the same as shown here. So that helps answer part A of the question, as well as part D, showing the schematics. So the pro-eutectoid phase is cementite. The schematics are as shown there. So let's go ahead and go back and work this problem. We're going to use this tie line beneath the eutectoid temperature first, and then we're going to work with this tie line above the eutectoid temperature to answer part B and part C. Let's go back and do that. So we've answered and shown A and D. Now, one particular nuance of this problem is that we're dealing in weights, and so we're going to have to use that mass fraction values that we've been calculating and use it in terms of weights. Let's go ahead and start that process. In B, we're asked how many kilograms of total ferrite and total cementite form. And anytime we see those terms, total ferrite, total cementite, that means we need to be working on that tie line just beneath the eutectoid temperature. Here, we're not differentiating between types of ferrite, for example, whether it's the pro-eutectoid phase or not. We're just using this value, this tie line, to give us, allow us to calculate total ferrite and total cementite. We're given that our system composition is 0.95. So I'm going to identify those lengths L1 and L2. So we'll get let's start by getting the fraction, the mass fraction of total cementite. So using those lengths and the values associated with them, we can calculate the fraction of total cementite 0.86. Now to get a weight then, in terms of kilograms, we take the total system weight, 3.5, times our mass fraction amount to get a value of 3.01 kilograms of total ferrite. Similarly, we can calculate the fraction of total cementite. Of 0.14 using L2 divided by L1 plus L2, and it just confirms as it should that those values total up to 1, and we can go ahead, take that mass fraction times our total system weight to get 0.49 kilograms of cementite. Of course, we could have just simplified things and just taken our original system amount minus the calculated amount of ferrite to get the same value if we wanted to. But we've done all the calculations here, and those two values are confirmed. Now, I skipped ahead a little bit too much there. I apologize. So we've calculated the weight of total ferrite and total cementite, but we're also asked to calculate the kilograms each of perlite in the proeutectoid phase. We need to recognize here that the austenite that's present here as we go through that eutectoid temperature will completely transform to perlite. So if we can calculate the weight fraction of austenite, it should equal the weight fraction of perlite. And to do that, we have to work just above that eutectoid temperature. So what I've shown here is that tie line just above the eutectoid temperature, bounded on the left by austenite, bounded on the right by cementite, and the distances L1 and L2. Now we're trying to calculate the amount of perlite initially, and we can do that by recognizing that all of the austenite will transform to perlite. So if we calculate the mass fraction of austenite just above that eutectoid temperature, that will equate to the amount of perlite that's going to form. So in terms of L1 and L2, I can calculate that the weight fraction of austenite is 0.97 and recognize that this is also the weight fraction of perlite. Taking the total system weight times that mass fraction, I can calculate that I've got 3.4 kilograms of perlite, which of course includes the lamellar structure of austenite and, the ferrite and cementite. So that means that the remaining fraction, mass fraction, has to be pro-eutectoid ferrite. Or 0.11 kilograms. I went through the same process here to show that the remaining amount that isn't perlite has to be the pro-eutectoid phase. And that was just a slight rounding error. It should total up to 3.5. The total system amount. I have a mistake here. This should, the pro-eutectoid phase is cementite. So make a note of that. In 9.65, we're asked to compute the mass fractions of pro-eutectoid ferrite and perlite that form in an alloy containing 0.35% carbon. In this case, it's very similar to the previous problem, except we're working with a hypoeutectoid steel. Here's the relevant diagram, figure 9.29, showing the decomposition of austenite from point C to point F. We're working with a carbon concentration in this example of 0.35. And so we'll calculate the requested value for the mass fraction of the pro-eutectoid ferrite and perlite by working just above that eutectoid temperature. This will allow us to calculate the amount of the pro-eutectoid ferrite and the perlite that forms from the decomposition of austenite. So let's go ahead and do that. So I've shown that tie line that exists just above that eutectoid temperature, and it's bounded on the right by austenite, bounded on the left by ferrite. Once again, recognizing that that austenite will completely transform to perlite. So if we can calculate the mass fraction of austenite, in turn we're calculating the mass fraction of perlite. So we'll take L1, divide by L1 plus L2. Then we can calculate the mass fraction of perlite is 0.44. We're asked to also calculate the mass fraction of the proeutectoid ferrite. So we can just use that distance L1 divided by L1 plus L2. And of course, these two values should sum to 1, which they do. Just confirming that we've done this calculation correctly. So there, looking back, we've got the mass fraction of the proeutectoid ferrite, and we've calculated the mass fraction of pearlite, which of course includes both ferrite and cementite. Problem 9.67 says that the microstructure of an iron carbon alloy consists of proeutectoid ferrite and pearlite. The mass fractions of these two microconstituents are 0.174 and 0.826 respectively. And we're asked to determine the concentration of carbon in this alloy. So let's take a look at the relevant phase diagram. In this case, we're looking at the example of the decomposition of austenite to proeutectoid ferrite and pearlite, and so we'll want to focus on this tie line just above the eutectoid temperature, and from that we can calculate the system composition and allow us to calculate the proeutectoid ferrite that forms up here at these grain boundaries. So we're working with that tie line just above the eutectoid temperature. In that two-phase region, then, there's austenite and ferrite bounded 0.76 on the right end of the tie line, 0.022 on the left side, and we're asked to calculate this system composition of that's present. Defining the lengths on either side of that unknown system composition as L1 and L2. I can calculate the weight fraction of the proeutectoid ferrite, L1 divided by L1 plus L2. But I'm given that the mass fraction of the proeutectoid ferrite is 0.174, so I can solve for x, the unknown system composition. And in doing so, I find that the system carbon concentration is 0.63% carbon, which is less than that eutectoid carbon concentration, and confirming that we've indeed done the calculation correctly. Here we're somewhere about 0.63% carbon. excuse me. In problem 9.68, we're given that the mass fractions of total ferrite and total cementite in an iron-carbon alloy are 0.91 and 0.09, and we're asked if this is a hypoeutectoid or a hypereutectoid alloy. Once again, if we see these terms, total ferrite, total cementite, that'll mean we're going to work beneath that eutectoid temperature. In other words, we're going to use this tie line, and we're looking for some unknown system composition X. So there's that same tie line showing L1 and L2 bounded on the far right by cementite, bounded on the far left by ferrite, unknown system composition X. We're given that the total ferrite mass fraction is 0.91. So we can set up our mass fraction equation using L1 divided by L1 plus L2 and solving for the unknown system composition X. We calculate a value of 0.62 weight percent carbon, which is less than that eutectoid composition, meaning this is a hypoeutectoid steel. In problem 9.74, we're asked to compute the mass fraction, or given that we're working with a 1% carbon steel, we're asked to compute the mass fraction of eutectoid cementite. In other words, the amount of cementite that's existing in the perlite, existing as perlite. So let's take a look at the relevant diagram. In our case, the weight percent carbon is 1, so slightly lower carbon concentration than shown in the figure, but the decomposition from G to I is exactly the same mechanisms. And so we're going to first find the total cementite below the eutectoid temperature. And then we're going to have to subtract off the pro-eutectoid cementite that forms to give us then the eutectoid. So we're going to take the total minus the pro-eutectoid cementite will give us the eutectoid. Let's go back and do that. So I'm starting working just below that eutectoid temperature, and I'll get the total cementite by using that tie line bounded on the right by 6.7, and my cementite on the left bounded by ferrite. So I'll go ahead and get the total, the mass fraction of the total for the cementite is L2 divided by L1 plus L2. Or a mass fraction of 0.146 is the total cementite. Now, next I'm going to calculate the pro-eutectoid. In other words, the cementite that formed above that eutectoid temperature. So I'm going to have to work with that tie line bounded on the right by cementite, bounded on the left by austenite. I'm going to go to the next page, get some more writing room. So I can calculate the pro-eutectoid mass fraction by using that lever rule, and it's 0.040. Now I need to get the eutectoid. I have to take the total cementite minus the pro-eutectoid values. Using the values I found earlier, the eutectoid cementite mass fraction is 0.106. And just showing again here schematically what I did. I calculated first the total cementite, and then I subtracted the pro-eutectoid amount to get the eutectoid cementite that's present in perlite. In 9.75, we're asked to compute the mass fraction of eutectoid cementite in an iron-carbon alloy that contains 0.87% carbon. So the relevant figure that we can refer to here is figure 9.32, showing the decomposition reaction of a steel containing, in this case, slightly greater than 1. In our example, we're at 0.87. So roughly at that carbon concentration, but the decomposition reaction shown in the figure is the same, so the schematics completely hold. And this is very, very similar to the last problem that we worked, in that we're going to have to calculate the total cementite below that eutectoid temperature. and then we will subtract off the eutectoid cementite that forms in the tie line just above the eutectoid temperature. And I think I called that eutectoid cementite. It's actually pro-eutectoid cementite. So let's go ahead and do that. And then once we subtract those two amounts, we'll be left with the mass fraction of the eutectoid cementite. So let's calculate the total cementite first. So I've drawn that tie line just below the eutectoid temperature, identifying on the right cementite at a concentration of 6.7, on the left ferrite at a concentration of 0.022, our system concentration of carbon that was given 0.87, and the links on either side of that lever point, L1 and L2, and I can get the total cementite then is L2 divided by L1 plus L2. So the total cementite that's present is 0.127, and that gives us the total cementite. From that, we want to calculate the mass fraction of the pro-eutectoid cementite, and we can do that. By working on that tie line just above the eutectoid temperature. So we're going to use the tie line that I just drew, bounded on the right by cementite 6.7, on the left by austenite at 0.76, defining our system composition of 0.87, and the links L1 and L2. I'll get myself some more writing space here. Using that tie line, I can calculate the mass fraction of pro-eutectoid cementite. And in doing so, I find that the mass fraction of the pro-eutectoid cementite is 0.019. And recognizing that the total cementite is comprised of pro-eutectoid and eutectoid cementite, I can go ahead then and rearrange that equation to allow me to calculate the mass fraction of the eutectoid. Using the value for the total cementite that I calculated on the previous page, plus or subtracting from that the eutectoid cementite that I just calculated, leaving me with the eutectoid mass fraction of 0.108 as my value.